Okay, let's start over again. So your lab number 5 has been released, and I'll speak more about it for Thursday. All right, I'll talk about it. Your written test number 2 will be tomorrow, and make sure you go to your enroll session. And then not much to say, and just make sure you study the cover materials. And then when you go to the room, just if I can start you guys earlier, I'll do so as well, so it can get some extra time. We'll see. And as for the bonus opportunity, it's completely optional. If you click on the link I included on the e-class, you will see that it will link you to the course evaluation that's formal. I cannot get access to any of them before I release the final grade, so it's completely anonymous. I think so far we're doing well, like about 30%-ish. But feel free, completely optional. Say whatever you like. I can only see your comments after the end of the semester. So, question? Yep, not programming test, written test. Unless you want another programming test. Okay, good. Okay, written test.
Website that you have, right? There were 2 slides with the proofs.
Yes, you mean the inference rule?
Yeah, the inference rules. Are we given that?
Yes, you'll be given that. Yes, exactly. Yeah, so guys, just for your information, I will announce that again tomorrow. So the way it's going to work will be, when you see the question there, if that require you to use the inference rule, you will have a sentence like, consider the inference rule covered in the lecture, and then you will see the desktop. So I will make sure I copy the file to the desktop of your computer. So if you look at the desktop, there will be a file consisting of all the inference rule. Yeah, a single page. Good. All right, anything else you want me to clarify? Good, awesome. All right, let's now do a quick recap. All right, and then we'll continue with the bridge controller. Alrighty. So let's see where we are from last time. And then we'll talk about some a little bit more challenging stuff today, which is nice. Okay. So we talk about the guard strengthening, especially we went over in detail the proofs. All right, one here and one here. If you're given such question in the, for example, let's say for the final exam, usually you will be given maybe a big sequence like this, and then you are able to, so you will be asked to really show the proof. For example, if that's provable, will show that you can somehow get stuck somewhere to show that it's unprovable, something like that. So of course, you wouldn't be given the inference rule over here. I'll speak more about your exam formats and some expectation, maybe either on Thursday or sometime Tuesday next week, right? We do have enough time to get you prepared. When you try the different proofs as exercise on your own, if you got a slightly different approach to prove it, feel free to show it to me. Maybe not by email. That it'll be much more effective. We can see each other in person or even over Zoom. All right, so just show it to me. I can double check for you if that proof works. All right, and then that's about the 2 proofs that we went over last time on Thursday. And we spoke about invariant preservation, and the ones that we spoke about was mainly just for old events. You can see we got a concrete version of ML out. We got a concrete version of ML in. So today we're going to formulate some very similar invariant preservation sequence as well for the new events. The principle will just be the same. All right, we'll see that. All right, make sure you know how to formulate the proof obligation, especially for the goal over here. You want to make sure you know how to formulate it. Okay? And the key will be to really apply the relevant before after predicate, right? So that's really something you want to pay attention to. Okay, I'm a little bit bothered by this tab over here. Okay, let me see if I can get rid of it. Okay, would it go away? Yes, good. All right, and then we talk about this in commuting diagram, and we're going to revisit this diagram again. So I will let you revisit the details about this diagram here. But just remember, the idea will be whenever we try to make a transition in the concrete model by using some concrete events, there should be some corresponding abstract transition as well for the abstract model. So both will be from the pre-states to the post-states. And today we're going to see some special case, right? We said that every O events, for example, MLL and MLN, they do have the abstract counterparts over here, respectively. However, what about the new events? That's something we'll see later today. There will be some counterpart as well in the abstract model, but some special one. Right? That's something we'll talk about. a little bit later today. All right, so exercise for you would be to try to discharge this particular sequence here and also this sequence over here. Of course, for your written test number 2 and for your exam, I would suggest when you try to do the exercise, try not to look at the hints if possible. And try to see if you can figure out exactly which ones are the relevant inference rule for you. All right, of course, if you come up with a different proof that's also valid, I can double check for you. All right, but anyway, so try not to rely too much on the hints. All right. And then for invariant establishment by the concrete model, that's something I'll leave you to really self-study. That one's really straightforward, all right? Because we're just initializing the concrete variable to just 0. So it should be very straightforward for you to actually figure out the answer, figure out the sequence. But the most important thing is how many sequences do you need for invariant establishment? It depends on how many invariants you need to establish. So that means we got 1, 2, 3, 4, 5. 5 of them. Okay, yeah, do the study and then let me know if you got any trouble understanding this. And to really prove this one and this one, very straightforward. Okay, usually, as I said earlier, for M0, when you want to discharge the proof obligation related to invariant establishment, usually very short. All right, and then here is a little bit like a summary about the layout. You got abstract events, and you got the concrete counterpart over here. And then today, we're going to focus also more on the new events. All right? There will be some problematic scenario that could be caused by new events, which we're going to see today. All right? Yeah, we're going to get to the term a little bit later. And this is where I believe that was the second last page we spoke about on Thursday. We try to work out the guard for IL in and IL out. The guards and also the action over here, right? So that's something I will assume you're kind of reasonably familiar with. So we can do more manipulation of the events. One more recap over here. If you look at the abstraction that we have for M1, typically, if a car wants to go out of the mainland, they will go onto the bridge if safe, and then they will go into the island. As soon as they go into the island, it will be represented by ILN. And then if some car wants to go out of the island, assuming that it is safe, meaning that there's no opposite traffic. So the IL out is going to happen, and then the car will go onto the bridge, and then when they got into the island, it's going to ML in, right? So ML out, IL in, IL out, ML in. That's a typical sequence for the events. That's kind of implicit. And we're going to manipulate it a little bit today. We'll see. All right. All right, so these are the two new events. And we talk about before-after predicates. So here we are only worrying about A and B. That means they are the variables being changed. That means C implicitly is not changed. That's why we say C prime equals C. So this will be very useful whenever you want to do some proof obligation related to invariant preservation. All right, that's something we have seen a few times. All right, that's really from last week. Any questions? All right, let's now move on to today's topic. So for today, let's start by thinking about invariant preservation for new events. That one there will be very straightforward, but it's also worth doing a bit. Okay, so basically for new events, okay, let's now talk about it. For each new event, IL in, IL out. So there is a special event that we can call its abstract counterpart. So let me now draw that on the diagram, and then we'll talk about what this event, how this event should be understood. Okay, over here. You know what? Beg your pardon. I'll talk about this one here in just one moment. Let me deal with this very quickly. Okay. So if you look at the slides over here, we really want to talk about invariant preservation. Let me see this one here. Okay, so that's the sequence. Got it. Sorry, I'm just slightly confused myself. All right, so let's start with this one first. Okay, this one here. That's what I want to do. Now, let's recall this commuting diagram, which I just recapped in the beginning. And we are now talking about two new events. The ones I'm talking about are IL in and IL out. So these are the two new events. All right. Apparently, in M0, there is no such event IL in. There's also no such event IL out. So now we want to think about whenever we want to make a transition by IL in, what should be the corresponding transition there in the abstract model? That's the question. All right. So now that's something I want to annotate. So what we are talking about here are about the new events. Okay, when we talk about invariant preservation, so now we are talking about the new events. And there are two of them, IL in, also IL out. All right, these two. And the way to think about, for example, let's say we want to make a transition of IL in, let's say, that's a new events. So what you can think about would be we have some concrete transition here. Okay, this one here, concrete events. And the example we're using is IL in. So this is a new event. Okay. What about the abstract counterpart? As I said earlier, there is no such event that's defined in the M0. So we're going to create an artificial event called skip. It's a very simple event. That event there simply does nothing. All right? Intuitively, thinking this way. IL in over here, or any new events, only modifies concrete variables. i.e. A, B, or C. That's something we know because there's a concrete event. It only modifies a concrete variable. So what about, does it do anything to the abstract variable here? Not really. All right. It would be as if the new events kept the abstract. Sorry, I'm just leaving out, running out of space over here, leaving the abstract variables intact. All right, this is really important insight. Okay. The new events kept the abstract variables intact. When I say keeping the abstract variable intact, this will corresponding to this particular abstract invariant skip. All right. So this is some abstract events simulating any new event. Okay, so what you can think about is whenever you got any concrete transition by a new event, the corresponding abstract transition will be a skip. I'll visualize that to you in just a moment. All right, this one here will just be skip. Now let's contrast something right away. All right, if you go back to the very first time that we spoke about this diagram here, which is over here, the same diagram. When we talk about a concrete transition over here, for example, it could be ML out. The corresponding abstract events will just be ML out, because we do have ML out in both models. But if we now use the same diagram to talk about transition for the new events, which I just introduced, which is over here. In this same diagram over here, if I talk about some new events which does not exist in the abstract model, if I try to do a new event transition in the concrete model, it will be corresponding to simply doing nothing to the abstract variables. So that's the new insight, or new event we're introducing. Okay. And of course, in the pre-state and the post-state, it will just be the same. So you can think about here, it would just be the pre-states. And this part over here would just be the post-state, and they should still satisfy the linking variance. That one doesn't change. And another important property about this particular skip event is what will be the before after predicate for that, right? Since it is some abstract events, so it should only supposed to modify abstract model, like an abstract variable. We only got n. But skip itself simply means do nothing. So it will be as if we don't change anything over here. So every abstract variable should really remain their value in the post states. So what you have is n prime equals n. So this is the before after predicate for the skip. All right. So when you look at exactly what ILN will do, for example, you can see here, ILN is going to, for example, decrement A, increment B, but its corresponding part in the abstract world over here is going to be just a skip, in which case we don't really modify n. All right, that's something we're going to visualize in a moment. All right, so far any question? So far what we have told you is you have to remember for every new events in the concrete model, their corresponding counterpart in the abstract model should be a skip. All right? And the skip does nothing. Let's see one example here, right? If you recall, in the earlier lecture, we tried to do ML out. So this concrete transition here has the abstract counterpart. That one's okay, because that's the abstract events. That's the old events. Now I want to develop this model slightly further. Okay, what I want to do is I want to do one more events transition. I want to do, let's say here, ILN. ILN over here. All right, that's what I want to do. And then this particular one is going to result in a post state in the concrete world. Let's put it here. So we got D is equal to 2. And what should be the action for ILN? Let's look it up very quickly. For ILN, it's actually going to decrement A and increment B. All right? So we're going to decrement A and increment B. So decrement A, so that'll be A will be from 1 to 0. And B will be from 0 to 1, and C remains 0. Okay, you see what I'm doing here, right? All right, so that would be the complete version for the concrete transition here. And we want to see what will be the corresponding abstract transition. By definition, since this is the new events, we're going to have a skip over here. And we're going to see if after the skip events, we got some post state here. Is the linking invariant still going to hold? If it doesn't hold, that means we have done something wrong. Okay? Let's now do that. So we got this one here is going to have a skip over here. All right, the skip here is really the new thing we are learning now, skip. All right? And over there, it's going to transition into this particular states. We got D is equal to 2. And for the skip, it's not going to remain the same for n. Doesn't change anything. So n will still be equal to 1. Just the same. Okay, skip simply does nothing. Are we okay so far? Just about the two transitions separately, right? One is going to do some transition on changing the concrete variables. The other one simply does the skip, which does not do anything to the concrete to the abstract variable. So you can see here 1 and 1, simply corresponding to the before-after predicate. Yes, question? Sure. The inside is like this. The new events over here is only meant to modify the concrete variables, A, B, and C. Okay? And then we know that strictly speaking, the new events over here has no abstract counterpart, because if you go to M0, we have not explicitly defined any events called ILM. That's newly introduced in the concrete model. So the way to work around it is by defining some events called skip. And the skip only exists implicitly in the abstract model. And that skip event is not going to do any impact to the abstract variable. And mathematically, it's still going to work because the invariance is still going to hold in the post states. That's something we'll see. Yeah. Yeah, untouched, exactly. So you can see the skip over here. If you look at the action part, it's simply empty. So that means the corresponding before after predicate, it will simply be n prime equals n, right? Doesn't touch anything. Let's say, for example, later on, we're going to see, let's say if we try to refine M2 into M3. In that way, M2 itself will be the abstract model. In that case, what will be the skip event in the M2, in M1, the abstract model? It will be, again, skip will be empty, but the before after predicate will be A prime equals A, B prime equals B, C prime equals C, right? Will be different. But that's for later, when we talk about second refinement. All right, so for now, we're going to focus on this skip events, which only exist in M0 implicitly. All right, so the final thing we want to be sure is this, and then I'll give you guys some exercise to try. Now, if you try to link these two states together, over here, right, these two. How do we link them together? It will be the same as before. We're going to look at invariant number 4, which will be linking invariance, right? That one there simply says, so that will be the linking invariance. Invariant 1, 4, which says that A prime plus B prime plus C prime equals M prime. What's M prime? M prime here is simply 1. What is A plus B plus C in the post states? Also 1. So the same. All right. So in the pre-states over here, we have the two states, concrete and abstract, consistent by invariant 1, 4. In the post states, we also have the same invariance linking both abstract and concrete also satisfied. So we are doing something consistent. So having the skip events nicely show the correspondence between the concrete new events and also the abstract part. All right. So that's the main thing that I'm trying to show to you so far. All right, any question here? All right, if no, I have some exercise for you to try. Okay, you can try it. If you want to check the answer together with me, we can do that later. Okay, let me now get a diagram here. I want to show you exactly how this is supposed to work. Let me just get a diagram here. There we go. Okay, the exercise I'll put in on a new page. Okay, over here. All right, so this is a diagram, and the exercise will be show the abstract and concrete transition of, all right, so this will be a trace. The trace in the abstract world will be in the concrete world. Let's start with that. We try some init to initialize the bridge controller, and then we try to do ML out. And then we try to do IL in. And then we do IL out, and then we do ML in. All right, so this one here is the concrete transition. What does it do, really? Imagine that if there is a car over here, as soon as the car goes onto the bridge, it's going to be ML out. And then when the car goes from the bridge into the island, it's going to be IL in. And there might be another car, could be the same car, let's say, the same car. And when the car decides to go back to the mainland, it's not on the verge between the island and the bridge. As soon as it goes onto the bridge, it will be IL out. And then when it goes towards the end of the other end of the bridge, and when it goes into the island, it's going to be ML in. Right? It's like a traveling. Right? So the sequence will be ML out, IO in, IO out, ML in. All right, so this will be a transition sequence. So what's really the corresponding abstract transitions? Let's write it down. It will be init, and then for ML out, what's the corresponding one? Also ML out, just the abstract version. All right, and now what about the correspondence to IO in? Skip. And then IO out will also be a skip. ML in, you got the correspondence. So you can see that very clearly. For IO in, IO out, you got skip and skip correspondence. Okay. And this part over here is the concrete transitions. Abstract. I really meant to say abstract. Abstract transitions. And what do I expect you to show? You want to draw some diagram like this to show that starting from init, you got some initial state over here, and between the two states that's corresponding to each other, they should satisfy the linking invariance. And then we have already done ML out, skip, ML out, IO in. You can complete the rest by doing more IO out and ML in, okay, to complete that and show the states. Okay. This will also be useful when we want to show how new events can go wrong. That's something we'll see a little bit later. All right, that'll be the exercise for you. Should be straightforward. All right, any questions so far? Good. All right, so far we spoke about the new events, and also its abstract counterpart will be the skip. And let's speak a little bit more about how to preserve the invariance. And then we're going to talk about this interesting phenomenon called divergence or livelock. We'll get to it here a little bit later. But let's now talk about invariant preservation. So whenever you talk about invariant preservation, it should be for both the old events and the new events. But just that in the lecture, we kind of separate them apart into part 1 and part 2, right? Part 1 was talked about last time on Thursday. So whenever we talk about invariant preservation, it should be applicable to both old events and new events. It should be both. But since for the new events, they have some different correspondent events in the abstract world, which is skip. So that's why we separate them for discussion. But the principle is really the same. All right, so why don't we do one exercise together? It's been a little while since we do invariant preservation. So let's say we talk about IO in. All right, let's do IO in over here. And then we talk about maintaining or preserving invariant 1,4, which is here. And then the nature is about invariant preservation. All right. And then this is the proof obligation, which should not be strange to you, right? That's something we have been doing. Okay. So let's now try this one very quickly. Okay. So we start with some axiom over here. So we're going to formulate a sequence. The axiom, which will be these two. So that will be D is a natural number and also D larger than 0. All right. And then we have the abstract invariance, which is over here. All right, it will be n is a natural number and also n less than or equal to D. All right. And then we got concrete invariance, which is over here. Concrete invariant would be all of them over here in the concrete model. A is a natural number. B is a natural number. Also, C is a natural number. I mean, we're running out of space, so I'll put it aside here. But if you see the slide, that'll be the correct way of putting it. Also, I got A plus B plus C equals N. And also A equals 0 or C equal to 0. So each one of them is a hypothesis you may want to use to show the goal. All right. And one more. this one over here is the guard of the concrete events that you're talking about. And this is the new events. Oh, sorry, wrong one. I'm meant to circle here. For ILN, we talk about A larger than 0, right? That's the guard. Also, A larger than 0. So how many hypotheses do we end up having? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of them, right? And then it's going to entail over here. Okay, we're going to say it's going to entail, all right, this guy over here. Okay, this one here will deserve a little bit more attention because the way we're going to replace the variables will be depending on what we just talked about skip. All right, that's important. Just don't forget, I'm going to put it here. ILN over here, this is a new events. At the same time, it corresponds to the skip. Right? Just remember that. And how do we figure this out? All right. This one basically saying go to JI, which will be the invariance that we are trying to preserve, which will be invariant number 4. And then you're going to apply the effects for both concrete and abstract events. So invariant number 4 is here. Right? We're going to write out the post-state version. Hey guys. Okay, we're gonna do this one here for the post-states, right? So that one there, I'm going to put a star over here, and then we're gonna figure this out over here. Okay, I'll put it down a little bit later. Okay, so this one here, if you try to put the post-state version, prime all the variables, A prime plus B prime plus C prime equals N prime. All right, the same as before. And what about the left-hand side? The left-hand side here is all about the concrete transition that's going to happen, which will correspond to over here, right? ILN. So A prime should be replaced by A minus 1. B prime should be replaced by B plus 1, right? You can see exactly the correspondence over here. And C prime would be implicitly just C, all right? Equals. Now, what about M prime over here? That's important. Before we actually got ML out corresponding to ML out in the abstract world, but now we don't have anything called ILN. That's exactly why I spoke about skip in the beginning of the lecture, right? Anytime you're doing any substitution for the abstract counterpart for some new events, you have to make sure you go to the skip. All right, so that's the critical thing. That's why I want to do the exercise with you one more time. All right, so now what you want to do is the skip that we spoke about here. That one has the before-after predicate M prime equals N. Right? It simply does nothing to the abstract model. So you're going to replace this one here, M prime, by just N. Sounds trivial, but it's important to get it right. Otherwise, you simply wouldn't know. Should I put N plus 1? Should I put N? Right? It simply corresponds to the skip. Right? Let me make some emphasis over here. So this one here is really about the skip. All right? That's really the most important thing. Okay, once we're done, so I can simply put the answer here. You don't need to simplify. You can just say A minus 1 plus B plus 1 plus C equals N. All right, that's the answer. Yes? ILN, that's the new events, which has the abstract counterpart being the skip.
So we're defining skip because when we were doing ML out, we said that the post-state of N becomes N plus 1.
That's correct. That's correct. So if you got ML out, for example, right? Again, let me make a final reference. It's important. Otherwise, you might be confused. If you look at, for example, over here, for concrete event that has the abstract counterpart, you simply look for the before-after predicate over here, right? Exactly. But now, since we talk about new events, right? So if you go back to the new events, let's go back to that model there. If you go to the new events, which is over here, sorry, ILN has no abstract counterpart explicitly in the abstract model. In that way, it will just be the skip, right? That's why you got to be careful about what to replace this by. Okay, good. All right, any question about this? So in the exam, for example, if I ask you to really formulate the invariant preservation proof obligation, the number one thing you want to clarify is, am I formulating the one for old events or new events? It's going to make a difference. All right. All right, so for you, this will be exercise to try to formulate the other one. I'll leave that to you. Exercise, and you can look at the answer also on the slides. And the question here, how many rules are we supposed to generate for M1 about the invariant preservation for new events? Apparently, it's going to be the number of new events multiplied by how many invariants we want to preserve. All right. So this one here is going to be the number of new events. In this case, we got 2 of them, multiplied by the number of invariants, which will be 5. 1, 2, 3, 4, 5. So 10 of them. Combined with the old events invariant preservation, we got 10 plus 10, 20 in total. Right? That's for your reference. When you study for the exam, just be clear which 20 invariant preservation proof obligation we're talking about. 10 of them are about old events preservation. 10 of them right now are about the new events preservation. All right, any question here? All right. If no, let's now move on. So this is the first proof obligation that we just formulated, right? That one, I'll leave the proof to you. You can take a look, and then you can also try to look at the solution on the slides. But if you can figure out another kind of proof by yourself, show it to me. We can take a look, okay? And then this will be the second invariant preservation. I'll also leave that to you to prove. This one might use a little bit more rules to really show it's provable. Okay, exercise for you. Again, solution is on the slides. All right. Okay, that's the transition that we just did. And that's the exercise for you. All right. Okay, let's now talk about something before that question. So say it again. I don't quite catch you. Mm-hmm. Yeah, so whenever you apply, let's say arithmetic, for example, here, of course, normally, if I give you any hints, I don't really say arithmetic, right? But let's say if you do want to apply arithmetic, you just got to be very clear. Am I applying, for example, to this particular hypothesis, which is usually the case. But if you want to rewrite the goal using arithmetic, that's also fine, either way. Any logical expression that you see in either the hypothesis or the goal, you can definitely apply arithmetic, yes. But you got to be clear which part you're applying it to. All right, that's good. Okay, let's now move on. And I want to talk something about divergence. And once we talk about divergence, we can introduce some very interesting modeling component called variance. All right. And before that, I would suggest we take a short break by taking attendance, and then we'll start you fresh after the break. All right. All right, so let's now continue. So before the break, let's see where we have covered up to the for the slides. So we have done this about invariant preservation. And just remember, we got something called skip, right? If you look at the slides, they also give you some textual description about the skip. And then we talk about invariant preservation for the new events, and that's what we spoke about before the break. And that's the first proof obligation, and that's the second one. And just notice that I only gave you 2 of the 10 proof obligation that's supposed to be there. So if I ask you for other ones, you should also be able to do it, right? Just make sure you also practice them. All right, so that will be one of the proofs. That will be the other one of the proof. That one's slightly more complicated, but not too bad. Okay, that'll be it before the break. All right, so now we're going to talk about something called livelock as opposed to deadlock. All right, conceptually speaking, so if you remember when we talk about the deadlock concept back in Model 0, deadlock simply means the system cannot make any progress further by taking any events into occurrence, right? Because all the guards for the events are disabled. Livelock is kind of the opposite, which is also bad. Livelock simply means you're going to have like a loop of events occurring over and over and over, such that no other events can ever occur anymore. So that's called livelock. A little bit like a BC loop that you actually spoke about in 2032, 2031 in the C course. But that's something I'll draw to you by using some example. So the easiest way to really have you see how livelock can really occur is by using some little bit contrived artificial model. So I kind of modify our M1 a little bit into this model here. Let's take a look, okay? This one here. Okay, this is the model that we have over here, all right? The main thing I changed was I got rid of some invariants. I also make the 2 new events unconditional, meaning that they can just happen all the time. All right? It's a possible model, but we want to see how bad it is. It's going to exhibit some behavior called livelock. All right? Let's see exactly what I mean by livelock. All right? Let's now take a look. Okay, let's just make some annotation here. So these over here are the O events, ML, MLN. So these are the O events. And these 2 are the new events. And the livelock is by definition going to be caused by the new event somehow. But we're going to see exactly. So these are the new events. Okay? And then notice that these 2 new events, they are unconditional, just no guard. They can happen just anytime. All right? And let's now take a look at some transitions over here, right away. So I'm going to put them like a side by side, or like a up and down, so you can see the correspondence. So we talk about abstract transition. And we also have the corresponding concrete transitions. Let me start with the concrete transition, and then we'll see how bad once we see the corresponding abstract transition. Okay, that'll be the order. Let's have the following. Let's say we have the init. Okay, you know what? Let me also have the help from this particular diagram, so you will see even more visually what's happening there. I'll put it here. Okay, right here. All right, so we got init. And then, let's say after the initialization, we have the first card leaving out of the island, which is possible, right? There's no traffic going to the other side, so there's no possibility of crashing, so that's okay. ML out. All right. So let's say after ML out, we basically have one car that's actually on the bridge heading to the island. All right. And given that these 2 events are guardless, unconditional, I can now run into a loop. Basically, it's going to be something like this. I can have IL IL in, IL out, IL in, IL out. It's going to go indefinitely. Right? So basically what's happening here is somehow the new events can just keep happening. And the old events never get a chance anymore to really get into it, to intervene. Right? If you check the guard, you will see why. So what we have is, visually speaking, this car over here goes into the island, ILN, and it tries to go back to over here, but without touching the mainland, it simply tries to go back to the island again, and then try to exit from the island and go back to the island again, and keep going indefinitely. All right? That's definitely possible by this particular concrete model that we have created. All right? So what you want to notice is over here, when we got this particular loop, this one tells you that the new events occurring indefinitely. And the old events simply has no chance to really intervene. Question? Yes. Yes. Exactly. So remember here in this particular model over here, ILN, IL, they have no guard. That means they can happen at any time. So there is one particular scenario for the model which will allow the car to say, now ILN, so after ML out, there's one car over here. So if we do ILN, that car goes into the island, and then since IL out has no guard, now it can also go out of the island and go to the bridge, IL out. And then before it touch back to the island, back to the mainland, you can also try to do IL in again. Go back here and then IL out. Just keep going, basically traveling. That's what's happening here. This is just one possible trace. But whenever you got problematic trace, just single one is enough. All right? All right, so here, concrete transition. So this is a possible trace that is problematic. All right. What you can try is this. Of course, I already modified the model such that there are simply no guards for IL in, IL out. If you go back to the original M1 I gave to you, it's simply not possible to have IL in, IL out, simply go indefinitely. It's not possible. But it is possible if I change the guard over here, right? So one possible question could be, I give you a model, and then I simply ask you, is it possible to have something called livelock for this particular model? So what you're gonna really try to find out will be, give me a witness trace, such that at some point it is possible to have the new events keep happening indefinitely. If that's possible, we have a livelock. And why is that called a livelock? Let's now take a look at the abstract transitions, how it's gonna correspond to. Right? Let's take a look. And then if you look at that, init is simply init. ML out has its correspondence, ML out. But now, remember IL in, IL out, IL in, IL out. They're all new events. What's their correspondence? Skip. Skip, 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 and skip, etc. So from the abstract model's point of view, this particular transition here is very bad. It basically, after ML out, the computer seems to be doing something very busy, but not very meaningful. It just keeps skipping. If you see the correspondence over here. It would be as if, from the abstract world, over here, we have something like while 1. And then you simply do nothing over here. Busy looping forever. which is definitely bad. It's going to keep exhausting the computer resources until it runs out of memory. Right? All right, quick recap. Whenever you have a refinement, when you have some new events, you have to be very careful not really run into the so-called livelock situation. And the livelock situation is defined as follows. If you can have some concrete transition trace, you just need one witness to show livelock. If in that particular witness trace, at some point, starting from that, you can have an indefinite loop between the interleaving of new events. Then you have a livelock. Because the corresponding abstract transition over here simply shows skip, skip, skip all the way. That's basically corresponding to BC looping that we are familiar with. You definitely want to avoid that. So livelock is not really achieving anything useful. It's simply just going to consume the resources of the system without achieving anything useful. As opposed to deadlock, you just cannot achieve anything either because nothing can be done. Right? So both deadlock and livelock are not good. All right, any question here? All right, let's now take a look on the slides. All right, so that's the trace I just spoke about over here. And then that's the corresponding abstract transition over here, showing that we got some BC looping from the abstract point of view, which is not good. And then we call this either livelock or divergence. Okay, either way. Okay, it's different from deadlock as well. All right, but none of them is actually useful. So you want to avoid both. And the follow-up question would be, how can we avoid livelock? All right. So the idea would be, let me go back there and I'll show you exactly how to do it. So we're going to start talking about something called variance. The idea goes like this. You want to somehow define your model in such a way that there is some measure you can have. And the measure is going to constrain the number of occurrences for the new events. That's something we want to do, all right? And then I'll give you exactly the measure, okay? The solution. Have a measure on imposing an upper bound on the number of interleavings of new events. For example, if you look at this particular concrete transition over here, IL in, IL out, the interleavings are simply not restricted. We haven't imposed anything useful just yet. But if we are able to impose such measure and show that the model diverges, we should be able to change it accordingly. All right? So that's really the intuition. All right? And the measure I mentioned over here is going to be called variance. All right? So that's something we're going to talk about right now. All right? It's like an upper bound on the number of interleavings. All right, good. Okay, let's now talk about variance. Let's give you some background information, just some intuition. So we're trying to talk about two things over here, and also I'll compare. So we have already learned about invariance. And we are now introducing another thing called variance. Both are useful for our model, but we got to understand exactly how to use them. Okay, let's now talk about them one by one. Invariance first. We know that invariant is basically like a predicate, a Boolean condition, true or false, right? It can be evaluated. It's a Boolean expression that should hold always. Or should always hold or always be preserved. That should hold, for example, after each event occurrence, right? That's something basically about invariant preservation. All right, and one way to visualize the invariant would be, let's now take a look at this diagram here. Okay. So think about this would be the invariant value over here is either true or false. So let's say the true over here, let's say 1 and 0. This would be true. And let's say 0 over here would be false. We want to make sure as soon as you actually try to initialize your system, the invariant should be established right away, true. After every event, invariant should remain to be true. So for example, you got ML out. For example, you got another ML in. Just for example, right? It should always remain true. It should be a straight line, basically. All right, that's about invariant preservation. It should always remain constant to be true. That's why it's called invariant, never changes. And the variance is actually some very interesting idea. Number one, variant is not a Boolean expression. It's an integer expression. Remember I said earlier, we want to impose some limits or upper bound on the number of interleaving. So that's why variant is going to be some integer or natural number. All right. All right, let me now write down some important takeaway for variance right away. So we talk about variance. So literally, variance simply means something that can modify, it can change its value over time. It is an integer expression. Integer expression that may change after event occurrence. All right, integer. So you want to notice that one would be Boolean, the other one would be integer. Okay. How do you understand variance conceptually? Okay, this will be the thing. So we have the diagram over here. Okay. So we got variance. Okay. And by the way, variance, what's the type? It's usually just natural number. It should never go below 0. All right, it's a natural number. All right. So, for example, let's say after the init, the value could be simply just 1 after the init. Just some value over here. The exact value doesn't really matter. It depends on how we define the variant for the model. But let's say conceptually. And then you may have some events over here. For example, ML out. Okay. That one there is more like O events. It may increase the value for the variance. All right. And then, for example, I might have some new events over here. IL in and also IL out. Each one of them is supposed to decrease the variance by at least 1 and then decrease. All right. And then we want to make sure every new event is going to decrease the variant value by at least 1. Because how the value will be, how high the value is over here, it should be finite. So there should be a finite number of decreases by the number of new events. So that means somehow it's bounded. All right, so that's something we will have to prove. All right. Okay, so let's now, you can think about that's kind of the curve. Over here and also over here. So this curve is a bit sketchy. So I think I will just draw the precise diagram once we see the precise variance. But what you want to notice is each new event's occurrence should strictly decrease. The value of the variance. So what that really means here is because the value for the variance can be only this high, finites. So once you start having the new events, can you still have things like this, like indefinitely? You cannot, because that'll be infinite, wouldn't it? All right. So that means you can only have a finite number of interleavings between the new events. In that way, you don't have livelock. All right. The number of new events interleavings is finite. That would mean no livelock. Right, just an intuition, right? So just want to remember, when you talk about invariance, it should always be true. For the variance, the value might fluctuate a little bit, especially the number of new events that might occur is really bounded by some finite number that's measured by the variance. If such measure cannot be shown to be consistent, our model will be shown as cannot prove some proof obligation. So there will be some proof obligation related to variance, which we'll see. Okay, we got about 10 minutes. I think that'll be enough for me just to show to you how we can plot the variance for some correct model. And that'll be it. Okay, and then we can try to formulate it on Thursday. All right. Okay, let's try to do it. We got 10 minutes. See what we can do. Okay, we go to, okay, so here. For now, let's assume, let's say I give you this. For our M1, the variance should be 2 times A plus B. Remember, A and B, they're simply natural number, right? So if I say 2 times A plus B, it's still going to be a natural number. I'm going to use this to measure how many times I can really have the interleaving for new events. I'm going to use this. Let's say take for granted. All right? And then I'll give you guys some exercise to try the different variants. Okay? Let's say we take this for granted for now. I really want you to see exactly how things can work with a particular variance. All right? And we're going to do some tracing. All right? We have our ML out, we have ML in, we got IL in, IL out. And this is the correct model without any livelock. We're going to see exactly how the livelock is not really exhibited by seeing how the variant value is going to change. All right? What we should do is we're going to try to trace this particular events occurrences. We got inits, we got ML out. That means two cars exiting from the mainland. And then we got IL in, the two cars going back to the island, right? IL out, so those two cars want to go back to the mainland. And then ML in, those two cars go back to the mainland, right, etc. Let's now try to trace the value change for the variance. So variant is basically some global integer expression that's going to measure if we're going to have livelock. That's really the intention for variance. And as we try, we figure out this tracing over here first, and then we try to plot diagram here, and then we make some general observation. Right? That's what we should do, hopefully. All right, let's try. Let's say after initialization, we know that both A, B, and C should be 0. 0, 0, 0. Right? You can see after initialization, I got A, B, C, 0, 0, 0. And what should be the variant value according to this formula? 0? Good. Okay. And after ML out, which is supposed to increment A by 1. Now I should get 1, 0, 0. And what should be the variant value now? 2. Agree? And then after the second ML out, I'm going to increment A further from 1 to 2, and B and C remain unchanged. Right? I'm still talking about ML out here. And the value for variance should be 2 times A, 4. Are we okay so far? I'm basically still doing the normal tracing for the variables here. But in addition to it, after I have got the concrete variables over here, I also try to calculate what's the variant value, which is the integer expression I gave you for you can take it for granted. All right. All right, let's now try the ILN. ILN, by definition, is going to decrement A and increment B. So I'm going to decrement from 2 to 1 and 0 to 1, and then 0. Agree? And then what's the new variant here? 2 times 1 plus 1, 3. Agree? Now I'm doing that together with you, very closely, but you should really also try to trace that yourself as well, right? I will give you some exercise to try later. All right, so what about after the second occurrence of ILN? Again, it's going to decrement A, increment B. So decrement A from 1 to 0, and B from 1 to 2, and then C remains 0. All right, so here we got 2 times 0 plus 2, which will be 2. And by the way, did you notice something here? The V here start incrementing until here, and then it start decrementing now. All right, that's something we got to plot to the graph. Right? Maybe that's something you have already noticed. All right, what about after IL out? IL out is going to decrement B and increment C. Okay, so here decrement B and also increment C. So 2 to 1 and 0 to 1. All right, so that one there, what should be the new variance? It should be 2 times 0 plus 1, which will be 1. Okay, another IL out, which means B will be further decremented, C will be further incremented, right? So we're going to have, so 0 here remain the same. B will be from 1 to 0, C will be from 1 to 2. All right, what will be the variant now? 2 times 0 plus 0, which will be 0. All right, and then after that, we got MLN. MLN is going to decrement C. So 0, 0, and 2 to 1. All right, and that one there is going to 2 times A, 0, plus B, 0, remains 0. It is okay for the variant value to stay the same, to some extent, but we're going to see the rule when we make a general observation. Okay, final one. If you try MLN over here, it's going to decrement C one more time. So we're going to get 0, 0 from 1 to 0. Right? And then if you try to calculate the variance, it's going to be 2 times 0 plus 0, which will be 0. Done. Okay? Are we okay with the first step? It's about tracing the variables changes in the transitions and try to figure out the values for variance over here. Okay? And I think I only got about 3 minutes. Let me start you with the plot over here. I will finish that on Thursday, but for those of you who really want to try to complete the graph, because that's really the way for you to see the patterns, I'll start you with over here. Okay, we got basically the value there. We got 0 over here. So, sorry. There we go. So we got 0. So we got 1. We got 1. We got 2. We got 3. And we got 4. Right? You can see the maximum value for variance is actually 4. So we got 0, 1, 2, 3, 4. And then what about the horizontal axis? It will be all the events we have over here, right? And we can have some naming convention over here. So for here, you want to say, what about after init? And after ML out, after second ML out, and then after IL in, after IL in, after IL out, after IL out, after ML in, and after ML in. So these are the vertical and horizontal values I would like you to try plotting. Because once you plot them, you will be able to generalize many patterns from there. That's the facts we need in order to formulate the sequence. Question? Yeah, so you mean the variant expression here, right? So it's something you have to say as part of your model, but when you actually state the proof obligation, you wouldn't see that per se. I'll speak more about it when I talk about proof obligation on Thursday. All right, so guys, try this one here, and then we'll continue on Thursday. All right, I'll see you in the lab tomorrow.